Good afternoon, folks. I'd like to welcome you to Physical Sciences Machine Learning Nexus. I'm Roger McWilliams, physicist by inclination, and I discovered coming in here today, I'm sure we'll learn some new science later, but there's already some new science. This clock used to be on the wall and is in the trash now, replaced by that. So apparently we now have time contraction.
Zing.
The smaller clock. Okay, so the machine learning nexus is getting set up now, and we have the delightful efforts of faculty and graduate students and other researchers and the Office of the Information and Technology here who are doing it. The elements that we've got going so far are described in this single slide. You can do your own photo of it or later pull it off the PSML Nexus. We're very excited to make a nexus, a place where people connect up and make a network to support the various machine learning, artificial intelligence activities that are going on in physical sciences. And we even have gracious support for this from various places in computer science and engineering for connecting as well, so that we don't really have too many boundaries. But we want to create an opportunity for focusing on problems in physical sciences that have various kinds of data science or related topics in them. As an example of how we know this is working, I did a look at recent physics graduates from our program, and about 20% of them have some kind of data science in their job titles now. So it's really getting very important. And we're finding physical sciences scientists have a tendency to do something for their own research, but may not know the methods or the problems addressed by others, which could help facilitate both their own research and new collaborative work. So we're trying to set up opportunities for faculty to mix, for graduate students to mix, all the researchers to mix, and create whatever is a useful network for you for machine learning broadly taken. We set up a few things to start. We have a faculty advisory committee. The names are all there, and several of the members are here. We have set up, and they've suggested a seminar series and even some speakers in the seminar series, such as the first one today. We have data science fellows, now one each in the 4 departments, and associated faculty advising them. Kieran Burke has decided or volunteered to help with a little more behind-the-scenes guidance and support for the 4 data science fellows this quarter, and we'll probably rotate it quarterly amongst some of the other lucky recipients that have data science fellows in the program as well. We'll have seminars every other Tuesday here at the 2 o'clock window. And we're setting up also to have a machine learning social hour, say Friday afternoon at 4 o'clock this week. We're going to try one out. This is not just a fluid dynamics experiment. It's an attempt to get people together and talk about the problems in machine learning they'd like to address. We had a boot camp already this last October, and we'll do something more along those lines. And we're opening up a lot of facilities, software, hardware capabilities with Domingos Badali and the Information Technology Group here for Physical Sciences. So we want this to be what you want to make of it. Our first speaker for the seminar series, if I try not to get too formal in this, we want conversations going, and our first speaker will be Professor Pritchard from Earth System Science. He studied at the University of Toronto and the University of Alberta, Edmonton, where Norman Rostoker's brother was a professor there for decades as well. Gordon Rostoker, I don't know if you've ever met him up there. And then got his PhD with Scripps, UC San Diego, and did a NOAA fellowship. He studies climate issues that go from global down to smaller scales. So I think multi-scale is a word. And he's been studying machine learning, particularly for cloud-related things, and I think actual real clouds, right? Not virtual. Well, he's doing both. And I guess he's going to talk about the combination today of both real and virtual in the machine learning. And then hopefully this seminar today will lead right into conversation questions that you folks want to get addressed today.
Okay, thanks. So I'm going to dive right in. A bit about me. So I have dual interests. Half of me cares about things like how clouds are going to reorganize in the future over tropics and esoteric issues of geophysical fluid dynamics, because the other half of me cares about things that deeply relate to that in terms of the fate of future rainforests and tropical cyclones and a changing climate. And I find these interests frequently overlap on the issue of confronting turbulence. A bit more about me. The tools I use for my research are standard global climate models, the sorts that governments use to make real-world predictions for policymakers. Prototype models that try to relax long-term problems with the way clouds are represented. Cloud physics are represented in these models that are entangled with large uncertainties on how hazardous my children's future will be. And machine learning, which I'm realizing is a great way to emulate and try to understand those cloud physics, as well as hydrodynamic models. So in any case, because we like to use these kinds of strange tools, we also try to explore new algorithms and computing infrastructure nationally, and that's what also opened my eyes to machine learning. And that includes helping develop climate models sometimes when the science demands it. Okay, so roadmap for this talk, I'm going to try to introduce you to this problem of why I'm attracted to deep learning for emulating turbulence in climate simulations. I'm going to tell you a story about my journey from being a skeptic to an enthusiast, from some surprises in trying to do this on a simplified aqua world. I'm going to talk about the exploding conversation happening in our field about everyone's thinking about this now operationally in the European Weather Community Center and nationally, the National Oceanographic Atmospheric Administration. So it's disrupting our way of thinking of how we do simulation. And then I'm going to talk about my favorite topic right now, which is the future. I think the way neural networks can be used now for interpretability as a new way to test hypotheses and do science. And then per Roger's recommendation, I'll try to end with a few discussion topics. But let's just dive right in. And please stop me. I'm used to talking to Earth system scientists. If I get lost in jargon, you're not going to be alone. Okay, but this is a classic graduate student diagram, log space time scale diagram. This is the overwhelming system we're trying to simulate in climate dynamics. There's 10 orders of magnitude in space and time. You're never going to simulate it all. So we have a hierarchy of tools, different scalings of Navier-Stokes that we apply to simulate different realms. The policymakers get to enjoy predictions from global climate models that have coarse resolution, 25 kilometers horizontally, 2 cores to represent cloud physics intrinsically, and therefore we have to rely on the evil art of parameterization, which I'll talk to a lot more about, which is the idea of attempting to represent inherently subgrid processes as a function of what you can resolve. Ill-posed, but necessary. But we have other simulations that are suitable for simulating small patches of atmosphere for short periods of time, large eddy simulations. And this is where I'm really interested in turbulence resolving simulations. And it might not be obvious why getting the details of turbulence right is important to the large scale questions of climate dynamics. So let me begin by trying to motivate that from a couple of issues that are near to my heart right now. So one has to do with low clouds. If you go to the beach and you see the edge of the marine layer there, realize that that represents one of the largest uncertainties about how hazardous the next generation's future is going to be, what those clouds do. Because if you look at pictures from space, animations off the coast of California, that marine layer is really just the edge of a planetary scale sheet of low clouds. It's blindingly bright. It reflects a lot of radiation from the planet, cools the planet. And it's beautifully complex. It has these spontaneous transitions from open to closed forms of cellular convection. These systems have been studied for decades with airplanes and boats and numerical simulations. We know a lot that these sorts of transitions that happen in low cloud organization depend in detail on the details of turbulent mixing and boundary layer eddies, and as well as the fine scale eddies that mediate mixing between that sharp interface of clouds you might have seen out the airplane window on the way to Hawaii and the overlying free atmosphere. And we know from holding simulations like these accountable to shipborne observations that we can simulate these physics plausibly for small patches of atmosphere. Here you're looking at what tends to happen to one of these cloud systems as it advex flows from cold sea surface temperatures near our coast to the warmer waters off Hawaii. It transitions from this kind of unbroken bright cloud system to this other exotic cloud system that has cumulus underneath stratocumulus, and when you view it from the top, you'll see that that transition's entangled with a broken cloud seed, a cloud seed that, like melting ice sheets, allows more radiation to intercept the planet where it can be absorbed. And so you know, many of us are wondering if climate change will entangle with these kinds of turbulent reorganization dynamics in ways that might cause these clouds to amplify climate change like ice sheets as they retreat. And on the other hand, they might also counteract climate change by thickening, because we actually don't know the sign of the answer right now. Okay, and you know, this should matter to any planetary dynamicist. You know, these details of cloud turbulent organization, you can also just tell from the satellite image, are entangled with brightness. Okay, so how bright a cloud is depends on its organization state. And, you know, brightness at top of atmosphere represents a horizontal gradient of energy, radiative energy intercepted. And that's what drives all fluid motions of the atmosphere and ocean on the planet. And nature being nature finds the most efficient way to do those sorts of energy transport. In our planet, we have the luxury of a triple point species that lives within the temperature and pressures of our atmosphere. And therefore, nature leverages the very efficient phase transitions of energy transfer. So all the kinds of motions that form our regional climate are entangled with cloud physics ultimately. Okay, so this is one of my main motivations for deep learning emulation, is this ongoing question of how will low cloud reorganization interact with climate dynamics? We know the process is ubiquitous in satellite observations. We know what it takes to simulate it. Those simulations already suggest for small patches of atmosphere that changes in organization could impact radiation at the top of the planet in ways that, unless buffered by the ocean, will demand shifts of rainfall bands that sculpt our regional climate. So turbulence matters. The other half of me, I live in an interdisciplinary department where I like to talk to ecophysiologists, thinks about the land surface. So these questions about how rainforests will change. This is also fascinating, but here's a close-up of a leaf, microscopic pores on a leaf. There's a chemical feedback that affects turbulence. As CO2 increases, plants photosynthesize through these leaves. That's where they get their carbon dioxide. And at high CO2, experiments convince us that these stomata tend to close. And what that means is that a plant can build itself while keeping its pores less open, which means they leak less water out the pores, which they'd rather not leak while getting CO2. But the end result is that plants are predicted to become more water efficient in a carbon-rich atmosphere. And you know, current climate models, you can incorporate these effects and convince yourself that turning up the CO2 and the warming effects that causes in the atmosphere, and as well as the feedbacks that it has on the ecosystems, produce this kind of a rainfall pattern. You know, less rainfall here, more rainfall there, where the blue colors are. And surprisingly, these forest effects are accountable, so the ecophysiological feedbacks are accountable for half the amplitude of the same pattern in the tropical rainforests. And it doesn't take long, I won't bore you with the stories that led to this diagram, to look at the physics to realize that the portion of the model that's predicting these effects from the forest ecophysiology is highly uncertain. So the physics that mediate the drying over the Amazon, for instance, are being orchestrated by these highly unconstrained parameterizations, that evil art, the modules that make lots of assumptions about unresolved subgrid physics. So the implication is to study these emerging vegetation effects on regional climate. You also can't escape details of turbulence. Yeah.
Do you tune those parameters based on data or based on the smaller scale simulations?
Both, yeah. But yeah, the ultimate, you know, there is no Navier-Stokes equation for a forest, unfortunately. So it's harder to tune an ecophysiological model than a physically based atmospheric model. But yeah, you tend to rely on data more heavily for ecosystem models. Yeah. So there are experiments that have sprayed CO2 continuously on stands of mid-latitude forest that some of these empirical parameterizations are pinned on. But it's a leap of faith to assume that those parameterizations, yeah. So this is the other half of my current motivation, is this idea that we know that plants become more water efficient at high CO2, and turbulence should respond in the boundary layer. That's a change in the surface energy partition, how much of the energy is balanced by evapotranspiration versus turbulent eddies. You know, current models suggest this is a profound effect, but it's very uncertain. So turbulence matters to planetary scales and to regional scales for climate. Okay, so where do we stand in global modeling when we're simulating planetary models of the atmosphere? So on the one hand, we have really exciting new tools for us, models that can produce animations like this. This is the current state of the art. Simulation like this can be run on large clusters these days. It's a global cloud resolving model. So for the first time as a community, we can resolve cloud elements globally. That's exciting. And you might be tempted to think some of this stuff you see off the coast of California resembles what I showed you in the satellite observations, but I want to convince you not to do that. because it doesn't take long to think of the grid resolutions of the current state of the art, 1,000 meters, and the scales of the eddies that form storms. You know, that's an appropriate grid resolution to simulate the deepest, largest tropical convective systems you might have seen out the airplane window if you've ever crossed the intertropical convergence zone. But when it comes to the kinds of clouds we live next to, these marine stratocumulus, we know the eddies that matter are much finer scale, 100 meters, like an order of magnitude less. And if you take into account the changes from the Courant limit and the time step you'd have to take, you can add it up, and it's like tens of thousands of times more computation will be needed to actually satisfyingly simulate these shallow clouds, most important to climate sensitivity, and we're decades away, probably 50 years away, if Moore's law keeps the pace, from doing that explicitly. There are ways to regionally nest grids, but you know, we don't have a really satisfying adaptive grid model yet. Low clouds happen intermittently with weather in the wake of mid-latitude eddies, for instance, so it's static. Yeah, it's difficult to come up with a satisfying objective rule for how to refine. It's controlled by the turbulence itself. So where we stand in global modeling is that, you know, on the one hand, we know the most important boundary layer turbulence processes occur at these length scales, less than 100 meters. And we know compute intensity octuples for each doubling of resolution, 2 horizontal dimensions and 1 time dimension. You know, so even today's most ambitious global cloud resolving models are kind of stuck near these resolutions of a kilometer. And we rely on other sophisticated parameterizations that have to make lots of assumptions about the unresolved equilibrium dynamics of cloud physics in these models. And any well-intentioned parameterization can fail in circumstances not envisioned by its designer. So unsatisfying approximations of turbulence seem inescapable today. So this is what excites me about the potential of deep learning. So deep learning might allow high-def 3D calculations of turbulence ahead of schedule. You know, climate simulation is always a trade-off between evolving computing resources and the amount of complexity of the physics you know you need to respect to do the system justice. Right now, my job's been hard. I have to hold myself accountable to the throughput needed to simulate the whole atmosphere for decades. That's what a policymaker needs, large ensembles of such simulations to do probabilistic inference. And from that view, satisfying 3D turbulence calculations seems totally unaffordable today. And therefore, in the kind of model I'll use, which is a multi-scale model, I'll tell you more about it in a minute, I have to make unsatisfying decisions like confining what explicit turbulence I can resolve to 2-dimensional planes unrealistically and only resolving the coarse scales of it. But if my job changes in the machine learning age to just producing short simulations that are just going to be mined for their physical essence to train an emulator, then that changes everything. It means that maybe I can do much more justice to turbulent physics today and upgrade my embedded models to what I prefer, high-resolution, 3-dimensional system, simulations that respect the physics. Okay, so that's the context. That's why I'm interested, is this kind of horsepower-limited tension in climate simulation. So let me tell you a story. Oops. Okay, yeah, so we're going to look at a simple feed-forward neural network. These are known to be, they're just powerful high-dimensional nonlinear regressors that happen to be easy to train nowadays thanks to GPUs and lots of software that's falling down like manna from heaven, right? So the question that we asked is whether or not this could be used to train a data-driven parameterization. So the inputs that I'll be receiving here are the inputs that a convective updraft cares about: the thermodynamic state of the atmosphere, the vertical structure of temperature on the one hand, which sets the dynamic stability, and water vapor on the other hand. This is the thermodynamic environment. And then the results will be, the output of the neural network will be what the job of a convection parameterization is to do, to predict as a function of that large-scale thermodynamic environment, that 100-kilometer scale environment, what the appropriate vertical redistributions of heat and moisture by clouds should be. Okay, and I'm going to do this in the context of a strange climate model that I like to work with. It's called a super parameterized climate model. And that means that it's a model that has 2 resolve scales, 2 scalings of Navier-Stokes, the usual planetary scale truncated at 100 kilometers, which neglects the non-hydrostatic terms that control vertical motions. And embedded with each of the 10,000 grid cells within that host model, which covers the planet, I'll embed a small sample of explicit convection. So it's strategically undersampling horizontal space in order to make these calculations globally affordable. So I'll confine my convection to an idealized 2-dimensional plane that's laterally periodic, that has the advantage that each of the embedded turbulence calculations can happen independently except after a 30-minute coupling timescale when everything communicates back with the host model. And what it does is it also gives you clean arteries to do training on. There's a clean causal relationship. It's like a predictor-corrector relationship between these two resolved scales. Okay, and this has been a fun model in the past decade. It's helped us map out the 1 to 4 kilometer regime that I showed you of an animation of before it was actually computationally possible to explore. And in the coming decade, I expect it to be just as relevant to probing the turbulence permitting frontier. Okay, and this is in the context of some others that are doing this in community with other training data sources. So, you could also take the kind of uniformly resolved high resolution simulation I showed you an animation of and imagine coarse graining it, artificially horizontally averaging it to derive statistics. I'm not going to do that. I don't prefer it. It has some causal ambiguities in it. The coarse graining process itself is difficult. And the trade-off there is that I'm accepting that I'm taking a model that has an artificial scale separation that doesn't exist in nature, but which also contains clean information about the scale that didn't resolve convection and what was needed to correct that. Again, please stop me if I'm getting into the weeds. I'm sorry. Okay, so just a schematic of the neural network. The inputs are low dimensional. There's 30 values of temperature for a local patch of atmosphere in space and time, 30 values of temperature defining the altitude dependence of temperature, 30 values of moisture, and a few energetic fluxes, sensible and latent heat flux at the bottom of the atmosphere, surface pressure, incoming sunlight. We're going to feed that in the front of a simple, crude, deep neural network, a feed-forward neural network, and our predictors, what we're predicting is a similar size vector that contains the vertical structure of the convective heating rate in kelvins per second and the convective moistening rate, as well as radiative properties of convection. Okay, so this is the question, is this viable? And I was skeptical 3 years ago that a dumb sheet of neurons should ever be able to emulate the actual partial differential equations of these cloud resolving models. But let me show you what convinced me. So we ran a simulation on an aquaplanet. It's zonally symmetric, so every longitude is the same, just for nice stable statistics. No continents, no complexity. We ran a year of simulation for training. We saved every single, for each of the 10,000 cloud resolving models at each 30-minute increment within that year, we saved the input from the host model and the output from the cloud resolving model, so the actual calculations. And then for the first year, we used that to train a neural network. So it adds up to about 140,000 double precision input and output pairs for each of those cloud resolving models across the year. And the question is, can those 140 million samples be used to replicate the actual predictions of these embedded cloud resolving models using a neural network instead? And after a lot of tuning and struggles, we eventually got a plot like this that convinced me, yes. So this is a R squared in the color bar. Blue is good. A lot of the variants explain. For the holdout test data set, the training data set, the second year that wasn't used for training, you can, and the y-axis here is pressure, so surface, top of atmosphere. This is latitude, south pole, equator, north pole. And in these important regions of the atmosphere where I know convective heating is most important for coupling to the general circulation of the atmosphere, we can coerce the network to get north of 70 to 80% variance explained. So that was really striking to me. It suggests quite possibly. Now you have to take the next step though, which is that's an offline process, right? So you have to then take that emulator, which obviously has imperfections, places where it was not able to explain the correct variance, and implant it back in the planetary model that used to have the actual calculation embedded within it, and ask yourself, what's the consequence of the nonlinear amplifications that can occur when you expose these kinds of imperfections to the Navier-Stokes equation scaled for planetary scale? And that was, this is just another example of the offline data set looking like a good prediction. But here's the prognostic test, we call that, when the neural network is coupling with the host model. Most of the time we tried this, it crashed and burned. But once it ran, and it was really provocative what it did. So it produced the same climate as the control simulation that had the actual convection simulations. So the emulated convection, actual convection, this runs 20 times faster than this, made the same mean climate, pressure, latitude, convective heating rate. This is the tropical, intertropical convergence zone, mid-latitude storm tracks. More importantly, I might expect a regression technique to lock onto the mean. More importantly, yeah. Yeah. I'm going to return to that. That's an important question. Thanks for asking it. Yeah. So this is just the more illustration of what got me interested. This chart especially speaks to me. So this is a 2D spectrogram where you imagine you're a satellite looking down on all the patterns of tropical convection burbling around on the planet. There's a lot of complexity there. Many coexisting classes of equatorial waves that are coupled to convective heating with different dispersion relationships. And this is a summary of what that dispersion relationship should look like. So this is time oscillations that are slower versus faster, larger versus smaller. And in the real tropical atmosphere, we expect to see footprints like this from equatorial convectively coupled waves that have this dispersion relationship, and an especially difficult to simulate signal that depends on explicit convection, the Madden-Julian oscillation. So when I saw the neural network model producing the same coupled equatorial wave dynamics as the control model, and none of the distortions we tend to associate with neglecting explicit convection, I got really excited. Okay, so that's the first half of the journey. Okay, so since then, we've been grappling with what this might mean to make a shift from the usual business of climate simulation to one that depends heavily on emulators. And let me just tick through a couple of the opportunities and quandaries that are emerging as we talk more about these results. So, you know, I mentioned this opportunity, high-def 3D turbulence ahead of schedule. It only took 3 months of that year of training data to get the skill, it turned out. So that says that, oh, if instead of having to simulate 50 years of atmosphere, I only have to simulate 3 months, maybe I could have done this again with really exquisite turbulence and succeeded. That's really exciting. So we haven't done that yet because I think there are other credibility tests that need to be passed. Because, you know, imagine, even if you could make this stable and robust, what would you sacrifice by relinquishing your physics to a black box emulator? I think we're still grappling with that. So, you know, this might be skill, but is it cheap skill? What do you lose? One thing you lose that could be important for climate is tuning knobs. So our old parameterizations of convection are deterministic subroutines that encapsulate our physical understanding of convection. They have knobs on them that we like to turn as scientists to learn about the interactions between convection and its environment. So for instance, you know, our cartoon models of convection that we normally rely on, you know, have a few parameters that make physical sense, and it's unsatisfying to abandon those just in terms of losing the ability to do experiments that teach us things. It's also unsatisfying because you expect things to go wrong when you couple an emulator inside a climate model. It will drift to a new attractor that will have to be tuned again to resemble the satellite observations. And how will you tune anything if there are no more knobs, if all the parameters are hiding inside of some black box, right? It's a real question. And I think the fluid dynamicists among us resist the idea of abandoning our cartoon models of convection because they really do encapsulate our understanding. We'd prefer to think of things as like a set of finite non-dimensional parameter groups that we can make sense of. On the other hand, I think there are those among us that think there's a strong philosophical case for the black box. You look out the airplane window at a picture like that might occupy the footprint of a standard climate model grid cell. And the degrees of freedom of that system might be too big for a human brain to encapsulate in a nice aesthetic interpretable cartoon. You know, and I respect those theoreticians in our community who have spent 30 years of their careers developing the world's best heuristic representations of convection, but who also admit that it could be one of 20 equivalently plausible formulations yet to be dreamt of. You know, there's been some pushback about the number of parameters our neural network had to rely on. You know, I think we had about 500,000 or 1 million parameters. So, you know, what's the point if it takes that many? Are we doing physics anymore? Well, I don't know. You know, if you read Francois Chollet's lovely textbook, Deep Learning with Python, you know, this really makes the case that we shouldn't think of the parameters in a neural network as ever trying to pretend to be the minimal number of parameters to define a system. They use the crumpled ball analogy. I don't know if you've heard it, but like imagine a classification problem in image recognition is equivalent to having a set of colored papers, a white and a blue sheet of paper on top of each other, and you crumple it up into a ball, and the task is to untangle them and flatten them out, right? Any of us would logically do that through a series of incremental geometric transformations that ultimately arrives, but none of us would claim for it to be the one minimal transformation, right? And I think that's the spirit of neural networks. They achieve their generalizability by incrementally decomposing a really complicated high-dimensional transformation into this set of iterative transformations. Okay, there's another deeper quandary. Okay, climate change is a small energetic imbalance at top of atmosphere, about 3 watts per meter squared. neural networks, any data-driven parameterization doesn't know about the law of energy conservation. And it doesn't take long interrogating the one we just trained to realize it has chronic mass and enthalpy leaks frequently higher than 25 watts per meter squared. 8 times the magnitude of global climate change. So that's obviously unsatisfying. So how to physically constrain neural network parameterization. So here's a wonderful project scientist in our group came up with a great way to solve this problem. He just writes our 4 constraints as conservation of column energy and mass, consistency of long wave and short wave radiative heating. We have 4 constraints. They happen to be linear. Convection is just something that redistributes mass vertically and heat vertically, but it can't create or destroy energy in the column. And you have obvious options for how to enforce these constraints. Ultimately a neural network is guided by whatever you put in the loss function in the optimizer, right? So, your optimizer might just be this skill in convective heating. But we could modulate the contribution of that, put a little alpha parameter in front of it, and also penalize non-conservation of our constraints if we can write them in a matrix form, right? And so, you might expect that works. You can turn this parameter and see what happens. This is an even nicer way, I think. So Tom devised this strategy to, instead of predicting all p elements of the vertical vector, to subtract 4 values and only predict p minus 4 values, and to inside the optimizer, upstream of the optimizer, do some TensorFlow wizardry and enforce the residuals to be accumulated upstream of the optimizer. So imagine this, like we're predicting fluxes of long wave radiation at top of atmosphere, as well as the vertically resolved long wave heating rate. And the integral of that has to match the residual of those by conservation of radiative energy. And so you could imagine, instead of predicting the full profile of long wave heating, I'll predict everything except the surface value, and I'll require it to be the residual it has to be. But I'll do that intentionally within the optimizer so that a stochastic downgradient descent has to find a solution that also obeys the constraint. And you can convince yourself it's possible to do that, at least for linear constraints, in a way that gets you comparable skill on the fit, but numerical precision on the residuals. So I was worried about that problem a year ago. I'm less worried as of 6 months ago. Okay, deeper quandary to your question, instability. Most of these neural networks, when you plug them into the actual host model, blow up like this. Ours happens to blow up like this. It makes bombs that just blow up in the mid-latitudes, and we don't know why yet. Others who have trained on other types of training data, like coarse-grained high-resolution simulations, they blow up differently. This is entangled with a technical issue. The modern software machinery of training neural networks happens in Python world. The climate model simulations happen in Fortran world. They're a little like oil and water. And there's been very little actual testing of these instabilities because of just the software barrier. So, and meanwhile, I think few of us in our community are using formal hyperparameter tuning techniques. So I've really enjoyed collaborating with Pierre Baldi's group. I highly recommend it. They've helped us learn how CS people do formal hyperparameter tuning, and that turns out to really matter. So here's a symptom of our instability. If we use the SGD optimizer instead of other ones, we have systematically worse behavior. Simulations crash earlier. And while we still don't have a magic cure that can fix all instabilities, we're starting to be able to map them out. And we're realizing how important formal hyperparameter tuning is. Meanwhile, they've also helped us build software that takes the pain out of plugging Keras-trained Python modules into legacy Fortran climate code to be able to perform hundreds of coupled runs that actually span the same phase spaces that the offline tuning does. Yeah. Yeah. Yeah, and I can tell you the journey over coffee, how we struggled for a year stupidly with an information bottleneck because we just weren't brave to go deep or wide enough. I think we were also entangled in the age where there wasn't a clean manual distilling the experience, but I really recommend Cholet's textbook. If we had it 2 years ago, we would have saved a lot of time. There are some things that seem to be working across disciplines, and I'm realizing that the CS collaborators are using the same workflow in high energy physics and genetics that they're using, and I can attest it's had a huge impact on our results in the turbulence world. So there's software called Sherpa that wraps around your Python script that just let it go on a GPU farm for 2 weeks, and I believe it's worth the wait. Meanwhile, this is so empirical, we need tests of physical credibility, right? So we're working to develop those. In convection, it looks like things like this. this is a diagnostic called lower tropospheric stability. It represents the static stability of the lower atmosphere. We know in the real world and in real simulations of convection, things like this should happen. As you increase that stability, convection should decrease monotonically and also shrink down to lower altitudes. So when your neural network does the same thing, you have a reason to begin to believe it's doing something physical. Likewise, we know that when you increase tropical vapor, convection should increase monotonically. But you know, it's unfascinating. It's so empirical, you have to sort of perform these credibility tests after the fact. This is another one I found very helpful. So this is, you take the neural network, which produces these heating and moistening tendencies. You can couple it to like a reduced order, not a planetary model, but like a linear gravity wave model, like a truncated model of the atmosphere where you can actually do linear stability analysis and produce a spectrum of the eigenmodes and eigenfrequencies, hunt for suspicious coupled modes. So here's an example here. This comes from our collaborators at the University of Washington, that they're training on coarse-grained output from a high-resolution simulation where they have snapshots every 3 hours. And it turns out there's causal ambiguity there in terms of the causes and the effects of convection. And they managed to figure out from plots like this that you know, convection is a bottom-up process. You know, vapor is transported upwards, but you can see the consequences of convection in the upper atmospheric vapor field, and the neural network can fool itself into thinking that should have predicted the causes of convection. And that turned out to produce these many unphysical, unstable modes we know should never exist in the real system. And by ablating the input vector to shield the neural network from being confused by these upper tropospheric vapor anomalies, they were able to remove the unstable modes, and consistently the coupled simulation ran a bit longer, but it still never totally avoided a crash. But I think that just speaks to the fact we're still assembling these tests of credibility. Okay, so where can we go from here? And just to finish this theme, to me, I'm really excited. I think it's already a surprisingly good emulator of deep moist turbulence. Even short simulations can be mined for their essence to create efficient emulators, including ones that obey conservation laws. So, you know, not many climate problems have been investigated with explicit convection, especially paleoclimate problems that require you to run cloud resolving calculations for centuries rather than decades. But I think that we can actually do that. It's opening up problems in the community now. And I'll get to this next theme in a moment. But yeah, you immediately start daydreaming about what else we routinely neglect because it seems like it would break the computational bank might be emulatable today. You know, for us, that's things like in-cloud chemistry coupled to cloud dynamics and species-level ecosystem dynamics, maybe ice sheet calving dynamics from full Stokes solvers, or you know, bootstrapping fictitious ensemble members in numerical weather prediction for better probabilistic assessment, more justice to cloud microphysics, the other elephant on the table. Okay, but I want to conclude the talk by you know, where I'm really interested in going these days. So neural network assisted dynamical analysis, actually doing science with neural networks. And I'll just begin by, you know, contrasting, or just begin by pointing out that we don't know a lot. A lot of our intuition comes from what computer scientists have done in the context of image recognition, right? I just want to point out how different our problem is. In what ways is the cloud parameterization emulation problem different than classical image recognition? Okay, so one has to do with data volume. You know, image recognition is usually trained on maybe 10,000 to 1 million imperfectly labeled human images, right? Here, I have orders of magnitude more double precision, perfectly known predictions. And so that's a huge difference in the data library volume and the quantity. And the dimensionality is totally different too. So an image, 256 pixels by 256 pixels by 3 colors, is, you know, 30,000 incoming values. There's no way to use the kind of crude neural network I used where we actually expanded room for interpretability and added a lot of depth in that context. It would break the training bank. They have to build bottlenecks. But we have low dimensional input, 3 state variables times 30 levels, 300 times fewer values. So, you know, I'm realizing as I talk to computer scientists, they have to kind of warp their mind a little bit to think about this limit. I think it's probably fair to say we don't know yet a lot about what's possible at this limit. And meanwhile, you start to think of the coping mechanisms that have to be done in image recognition to deal with the dimensionality of the input. There are convolutional neural networks, which have other advantages as well for classification problems, but they also involve dimensionality reductions that yield interpretability through this hierarchy of visual classifications. You can peer inside of a ConvNet and understand how it learned successively abstract representations of features, beginning with curves and dots that ultimately assemble into cat-like features that lead to skill. And you can't, it's irresistible to daydream about that, what that might, the analog might be there in my problems, you know. The relationship between convection and its large-scale environment is still an unsolved scientific question. What causes deterministic predictability of convection in the environment is something it would be great to use this machinery to explore. And there could be an analogy there with convolutional networks that we haven't looked at yet. But meanwhile, I want to resist the term black box as well. I'm realizing there's so much, the seeming act of emulation is actually deeply physical in the end, in surprising ways that are surprising me. So, you know, our purpose was pragmatic, but at the end of the day, you know, if the inputs and outputs are physically interesting, then the Jacobian that the neural network learns to train itself along is also interesting. So let me just explain this graph. This is what we call the dynamical response function, or the linear response function of convection. So on the x-axis here is the input, so the large-scale environmental temperature structure, thermal structure as you increase altitude, and then the moisture structure in this quadrant. So those are inputs. And this is response in the same units, but the rate of change. So how convection modifies the moistening rate and modifies the heating rate as a function of these inputs. And so the diagonal here just represents the fact that convection is a mixing process. It tends to remove moisture and mix it vertically, right? But then there's more interesting information in the thermal quadrants that tell you about cloud radiative feedback and the way convection conspires to produce top-heavy or bottom-heavy heating. So mathematicians can, like the part of our community that builds simple toy models of equatorial waves, they rely on pictures like these to inform their intuition. And they've been made before, but they're usually really hard won. And the way they're usually created is by taking a simple model, like one little instance of a cloud resolving model, running it out to a fictitious equilibrium that never quite exists in the real atmosphere, a radiative convective equilibrium, where you're justified to poke it with moisture and temperature anomalies and harvest the response and convince yourself it's quasi-linear enough to make a picture like this, but a powerful picture that tells you about growth rates. The neural network active emulating the same inputs and outputs bought me something far more general than this picture that I couldn't imagine another way of making, that lets me look how this familiar picture for the first time morphs as you exit and enter the warm tropics. Because it did the same thing, but for every possible basic state on the planet, including the deviation from linearity. So we could isolate the curvature and the deviation from linearity. And you know, we're just scratching the surface of realizing that the active training can lead to new diagnostics that you couldn't dream of looking at before. And then I want to conclude with a story from a colleague of mine who I think is really pushing creative ground. So this is a story, so we're going to abandon my pet interest of the emulation problem for now and the relationship between the convection in the environment, and turn to another really important topic in climate change, which is just detecting climate change from chaos in the observed period. You know, we struggle with this issue all the time. You know, part of what we see in temperature maps of annual temperature maps comes from the internal variability of the coupled ocean atmosphere system, of which there is one trajectory around its attractor in the satellite record. And part of it comes from the actual forced climate change problem. And when we run climate models, you know, they could be on any trajectory around that attractor. So here's an example of a temperature map. I don't know if you've seen a temperature map of what the geographic structure of warming looks like. It's higher amplitude in the Arctic, and there's a land-ocean contrast. So how can we tell which changes are signal from forced climate change and which are noise from inherent variability of chaos? So we have lots of ways to deal with that problem in standard statistical tools, but I really think this was a creative tack on it. So Libby Barnes at Colorado State University does something brilliant. She takes a large archive of simulations that have run like 40 different equivalently plausible realizations of the historical observed record. You know, and to map out the ensemble space of internal variability. They're each ensemble member is forced by the same climate change inducing boundary conditions, volcanoes at the appropriate times, greenhouse gas emission accumulations at the appropriate times. So they encompass the spread of chaos amidst the forcing. And it's a natural data source to look to. But then what she asked the neural net is brilliant. She says, I'll pluck one temperature map from 1 year in any of these simulations, And your job, neural network, is just to predict what year it was. And it's boring as an engineering exercise. You knew what year it was, right? But what Libby's realizing is that interpretable machine learning has come a long way, such that if the neural network can become skillful enough at detecting those geographic patterns of forced climate change that are deterministically predictive of the year, then you can nowadays, to succeed in this task, a neural network must learn regional signals that are reliable, in other words, distinct from internal variability across models and within observations. And she's taking advantage of layer-wise relevance propagation, which is an emerging algorithm, to take a feed-forward neural network once trained and hit it on the front to back-propagate how the output spreads to the input. So you might have seen pictures like this in the image recognition community. You can see a heat map of where a neural network that has been objectively skillfully trained to discriminate cats from other things looks when given any image. And here's an example of her latest paper on that just came out. So here's a random year plucked out of the observational record, the year 2000, anomalies from 1961 and 1990. And you can see like some high amplitude warming features that we might be tempted to think, I would have been tempted to think, were part of the reliable signal of climate change. But this neural network learned to predict that this map belonged to year 2000, and here's the heat map that showed you which parts of the world it was looking at to reliably make that prediction. And it was totally ignoring the high amplitude signal in the tropics because it's also entangled with extremely high amplitude internal variability there. And it was looking at the Southern Ocean where maybe changes in the ozone history of the stratosphere are causing migrations of the southern polar jet that are more reliable indicators of forced climate change, as well as interesting places. So you can now turn the machinery on its head and just train a neural network and say, hey, machine, where did you look in this overwhelmingly large input state vector, and confront your own intuition hypotheses. And it's pretty easy to set up the machinery to do that. So that's really exciting to me. I think it's clear evidence that interpretable deep learning is here. Neural networks are not black boxes anymore. They're tools to help visualize their decisions. And I do think that could be a game changer for geoscience research, where we often have overwhelming degrees of freedom and causal ambiguity between the role of chaos versus forced components of the system. And I'd like to emphasize that even these seemingly engineering acts of pure emulation are also entangled with new diagnostics. So we can use these things for more than just prediction. And the science can be what the network learns rather than the prediction itself. So I'll leave it there. I promised Roger I'd leave some discussion questions on the final slide. So here's a few, and maybe we can tick through them if we like, but I'll take any questions, and thanks for your time.
Question from you mentioned is low dimension in, low dimension out. So your network is very fully connected. It seems.
Yeah. We've been mostly experimenting with fully connected neural networks. Yeah.
What's the scale of the size of the network?
Like 100 in, 100 out.
So the number of parameters, right?
We've used anywhere between like 50,000 to 500,000 to 2 or 3 million. Yeah. But it can seem like a counterintuitively large network to use for such low dimensional inputs. One way to reconcile that is that we demand meticulous energy conservation. So the fit has to be really good. Yeah.
So have you tried to see even a smaller network can do a
smaller job? Yes. Yeah. Yes, that was our instinct. So I should mention, I started working on this project in my blue sky time with a colleague from Columbia who had used much lower dimensional networks to make progress in land simulation. And I think in hindsight, we wasted a year of time by restricting ourselves to a smaller. That was our intuition. We prefer something smaller, which is therefore more interpretable, shallower. But it was a visitor who was reading the latest machine learning literature who convinced us to go wide and deep, and I'm convinced just empirically that led to a step change in emulatability for these physics.
Yeah, that's also true in image recognition. You have to start with something big.
Yeah, more
to get the performance. But then after that, you can
compress. Yeah. So we're working on this now, and that's another tack on interpretability, right? Because if we could coerce the system to have the same skill with a big bottleneck in it, the system would have to find a latent space that clusters itself in ways that are deterministic of convection. So I'd love to I'd love to find that latent space. And we have a glimmer of a result that suggests we could put a bottleneck in here and get competitive skill, but it's early days on that front. I totally agree.
So you're saying the size of the network is the number of neurons in each layer, right? As opposed to the number of layers you're using?
It's both, yeah. So width and depth matters. So in hindsight, we used a narrower first layer than our input vector, which is a silly move for anyone. I realize now, but yeah. So you immediately lose information. If you immediately lose information in the first entry point of the neural network, you limit your possibilities a lot. So I'm realizing, I think a best practice for the first tack on the problem, if you're willing to throw horsepower at it, is to make a little more room and maintain that room throughout the network to be able to respect all the information that was there, and then also have a lot of room to create abstract geometric rearrangements of it, if you think that's important to your skill. But I totally agree, if you succeed in that limit, it makes a lot of sense then to try to see how far you can reduce the degrees of freedom in the number of parameters and still maintain skill. At first I thought these hyperparameters of width and depth were the most important ones to twill. But I'm realizing, we're confronting the fact as a community that not everything that seems predictive of better skill offline in this exercise actually ends up producing better skill online when you couple that thing inside the model.
Have you tried to put in shortcuts with that?
We've done almost nothing sophisticated and would love to. Yeah, sort of personnel limited. Yeah, but we haven't even explored convolution. It makes total sense to have different channels for the vapor and the temperature and allow different patterns to be found in those different channels. And at this stage, it's all personnel limited, free time limited. Yeah, but I'd love to.
So you showed us examples of things blowing up.
Yeah.
Right?
Mm-hmm.
So then you knew that things were working.
Yes.
But were there other examples where things did not blow up?
There is one, I'm afraid to say, only one really provocative example that I have in hand that really doesn't blow up. And I'm worried about that. Yeah, so we published a big paper a couple years ago that had this, and I don't know how the guy who manually tuned it happened across this configuration, but yeah, we have simulations that all the other simulations blow up at various points. So some survive for hundreds of days, which I think is pretty good. But others blow up, within 2 or 3 days. We are starting to see some mapping between decisions made in the optimization process and the proclivity to blow up. I started to speak to that. But yeah, I think it reflects the fact that we had some luck and are at the early days of really mapping out the parameter space that matters to the tuning. It's nice to know that a stable solution is possible, but it's really frustrating that it seems to be hard to find. Yeah, but I think
So some voting one.
yes, as far as I know, yeah, yes. So
I can't ask you, if you run the model on Wednesday or Thursday, right? You still get equally good fits, but hopefully you can.
I have one archived set of hyperparameters and reproducible workflow that did get the good fit. But redoing the exercise with a change that I didn't think would be consequential, in this case, increasing the degrees of freedom of each of the cloud resolving models embedded in the training simulation so that they're a little larger. We weren't able to replicate the result. But much more manual time was spent tuning that first exercise by the visiting graduate student in the second exercise. And meanwhile, the number of things we've tried to do offline is much larger because it's easy to do stuff offline in Python than the number of things we've tried to do inline. Because every time you retrain one of these Python networks, you have to go convert it into Fortran code and run a kernel. So there's this huge imbalance, and the business is so empirical. I guess this speaks to here. For us, it's been really important to beat down the software bottlenecks to try more things inline. So anyway, if anyone else finds himself in a similar situation, we have now a nice auto translator, thanks to working with one of Pierre Baldwin's students, that takes the pain out of testing really diverse architectures inline. But it's really the frontier for us where we're at right now in the whole business, is trying to understand the instability issue, and it's the logical thing to focus on. Unless this stuff can be the robustness properties of this can be understood and controlled, then, you know, I just feel like it's so underexplored that it's premature to say it's that dismal first experience should be predictive of what comes next. Yeah, I'm realizing how important formal tuning is and how little of it we do.
You're talking about Sherpa?
Yeah, Sherpa has been life-changing for me. So another adventure I didn't mention here is, you know, there's other credibility tests I'm worried about in terms of whether this will ever go prime time in climate modeling. I've shown you results from a boring aquaplanet that has very little diversity in its training world. You know, it's a boring world that has no continents, geography, seasons, diurnal cycles. We've been trying for the last year to replicate the exercise in a high degree of freedom world with continents and seasons, diurnal cycles, interannual variability. And poor graduate student who struggled for 7 or 8 months until we started working with Sherpa. And then Sherpa has produced, you let the GPU go for 2 weeks and it tests all sorts of things I wouldn't have thought to test, but things like gently introducing the learning rate, things like scanning across multiple optimizers, things like a 3-tiered process where you begin with a random search and then hone in on it. And we're still at the stage where we're looking at the offline fits of that more complex world, but they're finally competitive with what we saw on the aquaplanet that justified trying to implant the thing in couple world. Yeah. No, I'm rambling here probably, but are you getting a sense of the messiness of it? Yeah. Yeah.
So one of the first results you showed was after you did your simulation, you had the heat map of the R squared.
Yeah.
And my recollection is the red was 4 R squared.
Yeah.
And so at the time I thought, oh, that's too bad because your motivation was top of atmosphere radiation and Amazon, and that's where it was most red.
Oh, the boundary layer. Yeah.
But so I thought that was too bad, but then I thought, well, I don't actually know how the original model is doing. So maybe if it doesn't agree with you, that's actually great.
Oh, I'm really glad you raised this.
Yeah, and then so the other thing is with the picture, and there's a cat, we kind of know that that's true.
Yeah.
With the climate model, I don't know, the value in the like best, most sophisticated model might be 7, and then the neural network might get 7 or not, but 7 might not be the truth.
Yeah, so the heat map, I should point out, is not looking at really the truth scoring. It's assuming you have objectively convinced yourself you have a good ability to predict truth, and then you're asking a secondary question of where did you look in the input to get that score?
Yeah.
But I want to elaborate on your first question. I neglected to mention the system we're trying to emulate is inherently stochastic and turbulent and should not be deterministically predictable, especially in certain parts of the atmosphere. And so a feed-forward neural network, unlike the actual PDEs of convection, which contain a chaotic component that's initial condition sensitive, will always give you the same prediction, even with the same initial conditions. And yeah, we never expect it to predict everything, especially those things that we think are intrinsically stochastic. So when I saw that void of skill in the other boundary layer, you know, I was tempted to think, oh, that's the most stochastic part of the atmosphere, unless we tried to augment this thing with like a generative adversarial network that was capable of producing like conditional probabilities of specific submembers of the ensemble rather than just the ensemble name. We shouldn't expect skill there. But yeah. And that structure is also turning out to be very sensitive to the sort of world we use in the training data. So as we've added in continents and real geography, we're starting to see that lower atmosphere emerge as the region of highest scale. And that's probably because there's now a high amplitude solar heating cycle over continents with low specific heat capacity that is inducing a deterministic component of diurnal convection. So yeah, that's the wrinkle when you're emulating this chaotic fluid that you expect there, you should never expect to find perfect skill because there's no such thing. But yeah, to me, I guess a sort of a nuanced view of that map, we know from sort of atmospheric dynamics that there are regions, especially in the middle of the troposphere, you know, about 5 kilometers, 6 kilometers up, where convective heating is especially important to the energetic balance of the atmosphere in terms of generating the heating that drives the planetary scale circulations that determine regional climate. So I got excited when I saw those blue blobs in the middle of the atmosphere. I'm like, oh, that's where I know it should matter a lot. Yeah. Did I answer your question?
Yeah, I think so.
Yeah.
I just wanted to have a conversation.
Yeah, one of the first things we asked Pierre Baldy's group, like when he expressed interest in collaborating on this, was like, could we try to get the stochastic part again? And well, training camps is, you don't want to wish that on a PhD student, and it's pretty hard to coerce them to train. So I don't know much about that, but I'd love to try to predict more than just the mean and maybe a little bit of the distribution. I guess I had this question here. If anyone else is experiencing that, are there any best practices for how to do this practically beyond GANs? I've heard of variational autoencoders being helpful for this. Does anyone have insight into that?
What was the first word that PRD, wasn't it? Autoencoder?
Autoencoder is like, compression and building, and this issue of building the bottleneck and reducing the degrees of freedom needed. But again, I've seen it done for Rayleigh-Bernard convection. There's some people over at Berkeley Lab that have emulated Rayleigh-Bernard convection, and there the predictions are actually plausible chaotic ensemble members rather than the ensemble mean. So it's trying to predict the PDF, which would be attractive for climate.
Michael,
It seems harder.
could you guide a discussion on in-house software tools that people here might need?
Sure, yeah. Does anybody already have any stuck points? I could elaborate more on mine, but I feel like I've spoken a lot already here. But how many people feel like they have a painful software or hardware issue that's limiting their work on this?
I guess hardware, right? There are GPU resources that aren't using the quality group.
No, so I normally, for my computing work, I normally have to look external to UCI for the big clusters nationally. So my first, when I became convinced GPUs gave you a 10x speed up for the training workflow, I started looking at those, and they seem a little bit behind the times. But I was able to find a cluster at San Diego State, SDSC, San Diego Supercomputer Center. They have a bunch of nodes of like 5-year-old GPUs, K80s. Exceed is this NSF portal where anybody can upload a CP and ask for resources on these federally supported slices of machines. So we were able to get a bunch, like maybe 5,000 GPU hours there in exchange for uploading some of our science plan. I'm aware that the National Center for Atmospheric Research has a little GPU cluster, but I feel limited. Yeah, I've been trying to get my own little machine learning node built on the physical science computing infrastructure. NVIDIA is interested in the climate application, so they gave us a couple of free V100s, but it seems like Pierre Baldy, to do the tuning exercise has a GPU farm, and that seems really important. I don't know what else to say about that. It's for the data volumes here, we're talking maybe 30 gigabytes to 100 gigabytes for the training, and it's taking it used to be taking the student like 4 days to even try something. And since it's so empirical, it seems you need to be able to try things very quickly and iteratively. So that was unsatisfying. And we realized the GPUs knocked it down to maybe 8 hours or 7 hours. So it seems really important. I guess another issue is I don't know about how multi-node GPU learning works. That seems important too for these data volumes. I don't know if anyone here has intuition on what it takes to effectively, like how a problem size is big enough that it requires 4 or 8 or maybe multiple nodes of a GPU cluster to work on. I'd love to know. Seems like giving a student the ability to poke things at the frequency of 5 minutes instead of 8 hours would be very helpful in this empirical world. I'm also realizing that computer scientists are often dealing with much smaller data volumes that fit on laptops, and so I was kind of expecting to get some HPC guidance from the CS collaborators, but their first instinct was reduce the problem size for me to fit it on my laptop. But it's like, well, there's a lot of places on planet Earth, and most of them aren't raining in a given 3-hour interval, so you actually move that. Tens of gigabytes, unfortunately.
Do most people have larger data sets here in physical sciences?
How large is your data set? Like memory wise?
10 to 100 gigabytes.
Are you floating on memory, or do you have like a?
We mini batch it. So we mini batch it on samples of maybe 400 to 1,000. But yeah, I guess I honestly feel like I'm living in the dark ages. If I ever went to like Google or something, and they took one look at what we're doing and just laughed. And, yeah, so I'd like to learn about this issue. I keep asking students and postdocs about it. And, I'm aware of some, I guess a good place to evaluate would be like Lawrence Berkeley Lab, because they won that Gordon Bell Prize last year for doing a machine learning problem at scale on the world's best supercomputer that's just riddled with GPUs. But I'm scared that it seems like a lot of engineering work that there aren't handy tools to handle. But then again, I'm not doing it myself, so I don't really know. Seems like a good thing to have discussions about right now. Can I start with this bullet point? Is any of this like ring any bells with anyone? Do I is anyone else doing this this kind of thing in other contexts, like astrophysical simulation or other outsourcing physics to neural networks for computationally limited?
So my group has done some work kind of related, starting from the PD side. So you mentioned there are PDs in the atmospheric science as well. They are high dimensional, very expensive to simulate.
Yeah.
So one approach is to do dimensional reduction on those PDs, reduce them to low dimensional analytical systems.
You're trying to emulate a PDE solver?
Yeah. So of course, then you have to construct a smart basis to capture the molecular structures and so on.
Huh.
So there you use neural network to train.
Cool.
Dimensional reduction. So it's a different application.
Yeah, that's cool. I'm aware of this like Google Harvard partnership where it was really amazing. It was like, we all rely on coarse-grained discretized PDE solvers at the heart of our fluid dynamics predictions. And, we have the discretization we learned in grad school, like a centered finite difference or something, and it has error properties. You could ask I saw a paper where you just asked a neural network to come up with an optimal polynomial discretization for a PDE solution, and be agnostic to what it would be, and produce like really spooky convergence properties at surprisingly coarse resolutions. Is that akin to what you do, or different?
Your discretization depends on the solution.
Yeah, it's a solution-aware solver, right?
Yeah, you have to collect some samples from your solution first as training data, and then you can design the discretization. The classical approach would be independent solution. Your discretization is done ahead of time by humans, right?
Yes.
So from calculus or finite elements or whatever, spectral, use Fourier, given by Fourier. But now we build another function which is a priori unknown. You learn it from the solution itself.
So it respects the fact that the error growth properties will depend heavily on the nonlinear system and its dimensionality.
Or depends on the complexity of the solution. If your solutions are equivalent, then this basis will reflect the complexity problem, not like a pre-designed basis.
Very interesting, yeah. I didn't know that kind of work was happening.
Yeah.
What kind of systems are you simulating?
Passive scalar.
Passive scalar advection, diffusion?
A classical problem, Richardson, G.I. Taylor solved 100 years ago. You build
pretty far from the climate limit, but how many dimensions?
In our case, 2, because we have to run a lot of simulation of black data. But the idea is set forward. You can do 3 if you have enough. If you have enough, if you have a bigger machine, enough graphite.
So you feel horsepower limited to scale or algorithm limited to scale? Are you doing the 3D problem?
No, I haven't done 3D yet. This is for my next student.
Yeah. Is this hardware issue one of the bottlenecks, or not really yet?
If we could get the students to work on the supercomputer to collect the data, then the rest is there. Because you have to run the simulation.
So you're more limited by generating the training simulations.
Yeah.
By doing the machine learning. And are you doing a lot of formal hyperparameter tuning as part of this? Are you finding it important in the ways we are? Or?
In fact, we use DAM. So the one you
really?
Yeah.
Is it hard to train? This is a rumor.
Yeah, it is hard to train. But it's better than the VAE. The VAE doesn't work. We tried.
Interesting. Oh.
So answer the question you asked
again. Good. How many people here are grad students? How many of you are playing with any of the machine learning toolkit in Python? Over half.
I had a question on your data.
So your input did include latitude and longitude?
I intentionally avoided latitude and longitude because if I build an emulator of convection, I want it to be generalizable to new basic states. I don't want it to memorize this planet. And in fact, I didn't show it, but one of the important tests of the neural network for me to build credibility in it was to take the thing that was trained on the boring world that had complete symmetry around every latitude circle and to perturb it with a sea surface temperature anomaly that has a warm patch at one sector of the planet and a cold patch at the other. Like the real atmosphere, you know, the warmest water lives near the Indian Ocean and anchors the base of a planetary scale circulation called the Walker circulation. And that I expected that to fail. I was really provoked when it didn't. A, because that circulation didn't exist in the training data, and B, because the perturbation went out of sample in the training library. You know, I painted a hot anomaly on the hottest part of the atmosphere, so it took the inputs plus 3 Kelvin out of sample of the training library, but the thing still ran and made the right circulation. So I was a little spooked by that. I guess I'm learning in hindsight, you should never expect that kind of out of sample extrapolation from these high dimensional regressors that are supposed to just be interpolators. But sometimes it happens. That's really intriguing.
Well, I mean, it turns out that what you consider sort of extrapolation and interpolation is rather subtle.
No, totally this game, right?
There's interesting science there, yeah.
Yeah, but in fact, sort of a lot of our ideas about these are sort of more low-dimensional pieces.
Interesting.
So I go to a lot of talks at IPMAN, at UCLA, and lately they've been having quite a bit of machine learning stuff.
Yeah.
And this whole question, you know, we have intuitive ideas of what's extrapolation and what's interpolation. But I think most of them are not relevant. So what you just said, right? You know, are you like, how do you know how far you are out of your sample? Of course, that depends on your metric. And good luck finding your metric in this mess, right?
Well, I mean, I can know how far I can be out of sample on my inputs, right? Because I know the temperature span of the input training data set, and I can try to run that network in an environment where I've intentionally changed the lower boundary condition to take me X Kelvin beyond that boundary of inputs. So I don't understand the question about how do you know how far out of sample.
Well, because there's only just one of your, right?
It's entangled, it's correlated with many
How
other
far
things.
is that, right? You say, oh, very far, but, well, you know.
Yeah.
In terms of how the model is working.
Yeah. My postdoc or project scientist also was talking about the relevance of the activation function to the type of extrapolation you can get. I don't know if you thought about this, but for us, we've been trying to do this lately. So the original network I showed you there, it had specific humidity, which is not bounded by anything in different climates, unlike relative humidity, which always has the same bounds. They're on 100% in any climate. And we did some manipulations to cast the inputs in terms of relative humidity instead, and it totally changed the generalizability power of the model to extrapolate to a warmer climate. But we were expecting other manipulations analogous to that for the temperature to have similar effects, and they didn't. And now he's thinking that it's because we use this ReLU activation function. We know the moisture sensitivity is highly nonlinear. The temperature one, we have reasons to believe is more linear. And so maybe your intuition about the nonlinearity of the generalizability you desire should be baked into the choice of activation function. It's all anecdotal, and I don't feel like it's systematic.
You use the right, right?
Yeah, we tried a few things initially, but we sort of followed Cholet's guidance of what tends to work in most situations in the end. We use like a leaking ReLU because we have to predict negative definite quantities. That's why you can't eliminate the negative information. So are you working on this issue, or can you elaborate on your work?
No, just sort of when we first started, I worked with computer scientists at TU Berlin, and we entirely had been done kernel rate regression for our stuff. But you know, when we first started doing things, it was like, oh, you know, they don't want to extrapolate, right? And then they, you know, and then we sort of look at various things where we were, you know, allegedly extrapolating that things would always work, right? And then say, oh, well, you know, we don't want to get it probe, you know, the shape of the functions are far away. But we learned over time, well, sort of go ahead and try it out, right? And lots of the time it's working, and then over time, people are sort of realizing it's a very subtle issue as to whether or not, you know, what you mean by, you could argue that every time you run the thing, almost you're extrapolating. Because,
Yeah.
But even your test data versus your training data, right?
Yeah, so those are both subject to boundary conditions in climate simulation that constrain them to be within similar ranges. But we do other tests of generalizability I didn't mention, where we ask if an emulator trained on today's climate can succeed in predicting a warmed climate. And those tend to fail spectacularly, but much less so. You know, it was tempting early on to say, yes, oh, that's just because they're not extrapolators.
Yes.
There's a big zeitgeist out there that affirms that view, right? And heuristic though, right? And but yeah, I'm realizing right now that actually, no, they can extrapolate a little more than you thought if you bake a bit of physics into them. And maybe that's unlike random forests, right? Which should never be able to go off the convex hull.
Right. So a lot of things where people have said, you know, well, this looks like extrapolation, right? It turns out that it's much more subtle.
Oh, okay.
I mean, what I mean by extrapolation.
It's another nice tool to have in the arsenal. You know, like there's a deep history in fluid dynamics and finding non-dimensional parameters that are robust, right? But as soon as you think of the whole climate system and the complications of phase change, you know, it's like a holy grail to find something that would be climate invariant. But that's another thing I'm appreciating about the neural network is like the emulator and testing its generalizability as a sample becomes part of the new tool to try to hunt for such a thing, right? Bake in by strategically normalizing your inputs and outputs in ways that you think should transform the extrapolation problem into an interpolation problem, then it's another kind of empirical way to hunt for things that might be climate invariant. It's another thing I'm interested in. I see where.
I'm thinking maybe the Friday social will have some discussion and get the grad students talking a lot amongst each other as well. And I want to thank Professor Pritchard for doing the inaugural talk. Yeah, set the tone very nicely and walked off the gangplank just fine. Thank you very much.
Yes, definitely.
Very gracious of you. Deep into the void.